Welcome everyone to the another interesting seminar week from the SMaRT seminar series, which is jointly hosted by John Hopkins and IIT Delhi. So today we have a very young person, Arjun Puthli. So he is actually a final year integrated undergraduate student at the BITS Pilani, Goa campus, who is pursuing a dual degree in BE Computer Science and MSc Mathematics. As a part of his thesis, he is currently working as a research intern in the Department of Applied Mechanics at IIT Delhi. And there he is working on hybrid AI and foundation models for scientific computing. He is also an incoming PhD student in the Department of Mechanical Engineering at Purdue University once he finishes up his final project. His research interests currently focus on hybrid approaches that integrate machine learning with numerical methods to improve efficiency, scalability, and interpretability of the PD solvers. Today, he's going to talk about a work that he has done, which is on Neural Hodge Corrective Solvers, which is a hybrid iterative neural framework to solve PDs, I believe. So we'll hear from him. Over to you, Arjun.
Yeah, thank you, Professor Rajdeep, for the introduction. I'm really truly honored to be one of the speakers for this seminar series because I've been a regular attendee as well. So it's great to be on this end of the talk as well. So I'll be presenting my work that I did as part of my thesis on the Neural Hodge Corrective Solver, or NHCS for short. And just to go over what I'll be covering today, I'll be starting off with hybrid methods themselves and why we would be interested in them, followed by a mathematical overview or a brief overview rather of the Discrete Exterior Calculus framework and why we would be interested in that in a PD solver, and then go on to go over the method that has been proposed as well as the numerical results. And to conclude, I'll go over some of the limitations and future directions, as well as related work that I would at least like to bring to light that is relevant to the work that I have done as well. So, yeah, to start off, hybrid methods themselves are of interest to us because traditional methods that we deal with when solving PDs incur a high computational cost, even though we have very rigorous theoretical guarantees about the stability and their convergence. So when we are trying to solve PDs that have varying parametric conditions, it incurs a very high computational cost. And that's where neural operators or other neural architectures like Transsolver, etc., come into play. Uh, and these act as learned function space mappings. So even though there might be some mathematical intuition in their architecture, for example, in neural operators, we're familiar with the fact that the kernel layers are sort of analogous to a Green's function kernel. And even though that mathematical intuition is there, these still act as black box approximators. So hybrid methods come in by combining the adaptability of these machine learning methods and also the rigor and the stability that classical numerical methods provide. So to broadly classify these types of hybrid methods, you can bucket them into two types, that is DL assisted and DL guided. These are very broad categories and there might be a lot of in between and overlaps as well. But just for the sake of classifying these methods, you can do it in these two categories. So to go over DL assisted methods, the hybrid integrable transferable solver, or HINTS for short, is one such method and is going to be relevant later on in the presentation as well, because this is what we compared our method to, as it is also a DL assisted method. So DL assisted method, or methods that fall into this area, tend to use some data driven or neural architecture uh, to contribute to the solution of the PD, or the approximation of the PD solution. So in the case of HINTS, what goes on is that there's a pre-trained deep net, and this is coupled later on in the evaluation stage with a standard solver. So every few iterations, the deeper net comes into play, and the previous iterations residual is used as the input into the deeper net, And the output of the DeepNet is then treated as the correction term for the current iteration's solution approximation. So the DeepNet directly contributes to the solution itself. But on the other hand, in terms of the DL guided methods like the flexible conjugate gradient neural operator method, a neural operator is used to guide the FCG method itself. So what I mean by that is instead of analytically computing the Krylov update vectors, you're using a neural operator to do so, and using these vectors, you're updating the solution itself. So it's sort of guiding the method instead of contributing to the solution directly itself. Uh, Although we won't be going over this much later on, I just thought it would be relevant to at least mention it to give an example. Okay, so coming to discrete exterior calculus itself, our motivation is to use these discrete exterior calculus operators in a hybrid physics solver. So discrete exterior calculus itself is just the coordinate-free definition of calculus and all the notions that we are familiar with in uh, vector calculus. So the structures and the functions that we deal with in this formulation are known as K chains and K cochains. So while a K chain is defined as a linear combination of K plus 1 clicks, a more easy to understand example would be that a zero chain is essentially just the set of nodes in a graph or on a mesh. A one chain is just the set of edges, and a two chain are just the set of faces that we have in our mesh structure. And with these structures, there will be some values associated with these with the various points and the various levels of the structure. So what I mean by that is we would want to have functions that act on these k chains, and these are known as the k cochains. So a zero cochain is essentially just a function that assigns values to nodes. One cochain assigns values to the edges, and a two cochain assigns values to the faces of our mesh, and so on and so forth for higher levels as well. So essentially, it would be like a zero cochain acting as node potentials, a one cochain acting as edge flows, and so on and so forth. We also deal with these two operators known as the boundary operator and the co-boundary operator. A boundary operator takes a k chain as an input and outputs one at lower level, so the k minus one cochain. Sorry, the k minus one chain. So as the name suggests, it gives the boundary of a structure. So if you were to consider the figure on the right, if you were to take the entire triangle face structure and call it sigma, if you were to use the k is equal to 2 boundary operator, it would effectively just give us the lower level edges, which act as the boundary of that triangular face. So its name is quite intuitive to grasp like what it does. The co-boundary operator, on the other hand, takes a k cochain and gives us a k plus 1 cochain. So what this means is that if you have a cochain that acts on the edges, so E1, E2, and E3, and let's say you have alpha 1, alpha 2, and alpha 3 associated with those edges, then the co-boundary operator acts on that and gives us the phase circulation flow, or the cochain associated with the face of the structure. And together, these collectively give us the discrete Stokes theorem, which is the discrete exterior calculus version of the Stokes theorem that we are familiar with. And both the boundary and the co-boundary operators form a sequence, form an exact sequence, which means that successive co-boundary operations, or a more precise way to give to explain this would be if you have to take the co-boundary operator for k is equal to 1 and k is equal to 0, those successive operations would just give us 0. This is relevant because if you were to think of the co-boundary operator in a more physical sense, for the k is equal to 0 case, we are just taking edge flows. Sorry, we are just taking the node potentials and we are converting them into the edge flow associated with the edge between those two nodes. And for the k is equal to 1 co-boundary case, we are taking the edge flows and converting them to the circular phase flow. And what that intuitively means is that it's sort of like the gradient and the curl operator. And the curl into the gradient then gives us 0. So this exact sequence property preserves some of the preserves the vector calculus operations and properties that we already know. Most of the things that were discussed up until this point were purely topological in nature, and there's no sense of any metric relation between the structures that we're dealing with. The Hodge star precisely does just that. It introduces some notion of metric information into our framework, and this it does so by relating the dual of a chain complex and the primal complex itself. So the precise definition is in the next slide over here. I've taken it directly from the paper itself. Uh, it essentially constructs a diagonal matrix that relates each cell complex with its corresponding dual cell complex, or the measure of each of those. So uh, either the area, the length, volume, depending on what type of structure we're dealing with. And this also gives us the adjoint of our co-boundary operator that is known as the co-differential operator. But in order to do this, you'd have to construct the dual as well every single time. And this brings us to the idea of the data-driven exterior calculus framework, where instead of constructing the dual and then finding these ratios and then constructing the Hodge star operator itself, you're learning this metric information directly from data itself. So this paper by Professor Nat Trask who's currently at UPenn but worked on this during his time at Sandia Labs, uh, proposed the idea of the data-driven exterior calculus framework, where these data-driven diagonal matrices are used to learn the metric information through data. So these act as Hodge star surrogates instead of constructing them analytically. So each of these BK and DK matrices are essentially just that, and they the positivity is enforced either by squaring the parameter itself or by taking exponential or any other way. But we chose to do it using just taking the square of the parameter in our implementation. So what you can do with these operators now is you can construct a representation of the PD itself and then use that in a way to solve for your approximation. This work also introduced the idea of constructing the PD and also a neural network correction term that is mesh component wise. So depending on the type of problem that you are dealing with, you would have a neural correction term for either each node if you're dealing with node potentials or each edge if you're dealing with edge potentials. And these are shallow neural networks. And then in order to solve this, you have two main objectives. One would be to solve for the PD solution itself, and one would be to update the parameters during the training procedure. So uh, this was done using Newton-Raphson updates to satisfy the KKT conditions, and accordingly, both the solution and the uh, parameter updates were done in one loop itself. There are quite a few issues with this method, however. One is that you would have, however shallow the neural networks are, they're still mesh component wise, and this doesn't scale well. Furthermore, in the Newton-Raphson updates, there are quite a few Jacobian computations that would have to be done. And that means that would significantly increase the computational cost during training. And the training process itself is quite unstable because learning the parameters and the solution together can cause the loss to explode. So the initial parameters that were set for these operators and for the neural networks themselves might not be representative of the PD initially, obviously. And this can cause the solution to blow up. And that would mean that the parameter for the next epoch would not give us anything meaningful for the rest of the process. So in order to overcome all of this, we proposed the Neural Hodge Corrective Solver, and in this, we were able to show that it is much more scalable than this method. We reduced these component-wise neural correction terms into a single CNN for the entire domain. And we also introduced a staggered two-phase training process. So we separate the need to update the parameters and solve for the solution itself in a single loop. So in phase one, what we do is we minimize the relative mean square error of our operator with our ground truth forcing function information itself. So sort of minimizing the relative residual. And in phase two, what we are doing is we input this model into a hybrid framework. And since it is now primed on the data itself, we are able to, and have, it's a better representation of our PDE. We use this hybrid framework. We train it within the context of this hybrid framework for a few additional epochs to obtain a better representation of our model. So the hybrid framework essentially involves n initial Jacobi iterations to prime the approximation, and then additional Richardson updates using our model, where the update is done using the residual correction of our model. So if you were to look on the right hand side of this diagram over here, it is essentially the update rule involves the difference between our forcing function and the so essentially the residual itself. To compare the training cost of the two methods, the red line represents the phase one and phase two, the combined training time of NHCS for the largest model that we trained for, so the 64 by 64 case. And this involved 30 initial Jacobi iterations and then an additional 20 Richardson updates in the phase two part of our training process. The blue line, on the other hand, is the time taken for one epoch of the original training method. And we set a maximum number of 50 Newton-Raphson iterations. So if our solution were to not converge within those 50 iterations, it would just move on. And as you can see, by the time you reach the 20 by 20 grid size of 20 by 20, a single epoch of the original method already takes more time than our entire training procedure itself. So from a computational point of view, especially for the training procedure itself, we have already significantly outstripped it. For numerical experiments, we took three problems: the Poisson and Helmholtz equation and the elasticity equation, all in 2D. The Poisson and Helmholtz equation data was constructed using these Fourier-like expansion terms, where the coefficients a n were sampled from a standard uniform distribution. And in the case of the elasticity problem, we consider a square plate where there's a square hole in the center, the bottom edge is fixed, and we are stretching the top layer by some amount y naught. And the problem parameters over here are sampled from these respective uniform distributions, where the problem parameters are the Young's modulus, the Poisson's ratio, and the displacement of the top layer. Okay, so coming to the evaluation results themselves, as I said earlier, we compared our method to the HINTS framework, and the top row represents the runtime comparisons across various grid sizes, and the bottom row represents the evaluated relative MSE of our solution over various grid sizes for the Poisson, Helmholtz, and elasticity equations respectively. So for the runtime graphs, especially for the Poisson and Helmholtz equation, there's already a significant time improvement in terms evaluation time improvement over hints. But this is further highlighted in the case of the elasticity problem, where the hints framework requires significantly more time as the grid size increases, as the traditional part of the hint solver has to accommodate for the boundary of the hole in the domain. On the other hand, NHCS does not have to make the same accounting, at least in the Richardson update loop, because our discrete exterior calculus operators considers this as part of its structure. So we don't have to separately account for the hole or the boundary of the hole and any of the conditions there, because that is how our operators are constructed in the first place. And in terms of the relative mean square error in the results, again, there is a significant improvement as compared to hints. Although in the elasticity equation case, hints does perform better initially. We are considering a much lower frequency solution, a lower frequency solution problem in the case of the elasticity problem. And at the coarser grid sizes, the hints framework is able to significantly outperform NHCS over here. For more qualitative visual results, we have also just taken a few samples of, we have taken a sample of the predictions from each of the problems for each of the methods. And in the case of the Poisson and Helmholtz equation, I'll go on to the next slide for the Helmholtz equation as well. But for both of these, it's quite evident that NHCS is able to approximate the solution quite well. And although Hints is able to do a similar great job in terms of capturing the more prominent features, the central region, there's a noticeable over-smoothing that occurs. And this is true even in the Helmholtz equation, as I said earlier, where the more prominent features are being captured, while the more high frequency regions that are there in the center where there are more variations, that tends to get a bit over-smoothed. And this shows, again, performance gains that we saw earlier in the evaluation graphs. And in the case of the elasticity equation, which I find the most interesting of the three problems, the hints prediction is seemingly better initially, like at first glance, but again, it's just far smoother than the NHCS prediction, where coarser errors are visible. However, if you have to look more closely, the general approximation trend, especially closer towards the whole boundary, is much better in the NHCS case as compared to the hints approximation. And a few additional Jacobi iterations in the case of the NHCS prediction would like post the Richardson updates in the evaluation loop would actually smooth out these errors. So in terms of so despite the coarser errors that are visible in this case, as you get closer to the whole boundary, you tend to notice the benefits of this method, where it's geometry aware in a sense and is able to account for this inconsistency in the domain. So coming to the limitations, some of the potential solutions as well as future directions. One is scalability. So although it is more scalable than the data-driven exterior calculus framework training methodology that was proposed originally, there are still significant issues with the method because the co-boundary operator scales quadratically. And one potential solution would be that we could take some sort of domain decomposition where we take identical subdomains and then share the co-boundary operator across them. But the issue with this method would be we would have to restrict ourselves to regular domains if we were to do it in this method. Another solution would be to do another form of domain decomposition, except we take different types of subdomains, but again, we would be restricting ourselves in terms of the types of problems, the types of structures, domain structures that we can deal with. Another issue here is that there's no super resolution because the learnable BK-DK matrices that act as the Hodge star surrogates are constructed with the dimensions of the coboundary operator in mind. And because of this, and because you want to preserve the interpretability of these learned parameters, uh, this prevents us from really achieving at least super resolution in uh, our work itself. But one potential solution would be to fix the operator resolution and then learn an encoding onto this cursor mesh as well as the decoder back to the original size. Uh, and this is where some ideas from Transsolver could be used. For example, where uh, you sort of learn groupings of the various mesh components in the encoder part and then sort of do the inverse of that to get back our original output. And some future directions would then be to extend this idea to time dependent PDs and nonlinear PDs, and obviously improve the scalability as well. Some related works that I wanted to bring up as well, uh, in terms of geometry aware and geometry preserving or as structure preserving physics solvers. Delta pins is one such framework that was introduced a few years ago, where the eigenfunctions of the Laplace-Beltrami operator are evaluated at various points in the domain, and this is treated as the input to the pin. So instead of directly inputting the domain coordinates into the pin, you're instead evaluating these eigenfunctions at these points on your domain, and then inputting this into the pin. A more relevant uh, alternative way that uh, exterior calculus is currently being used is in the data-driven Whitney forms series of works that is being carried out by Professor Nat Trask himself at his group at UPenn. This is very, very similar. In fact, it's parallel to the work that was presented by Professor Yongshu Choi a few weeks ago in the SMaRT seminar series itself, where he presented his work on the data-driven finite element method. So this is essentially the same thing, but with a discrete exterior calculus framework in mind. And he has published multiple works in this area, sort of progressively building up on one another. And it's another interesting alternative sort of view to this area. And just to conclude, I've also included I've also just cited some of the resources that I thought would be relevant, especially the lecture notes by Professor Keenan Crane from CMU on discrete differential geometry. It's quite a useful set of notes and has helped me out quite a lot over the past several months. So I thought I would specifically highlight that. Yeah, I think I'm done. If anyone has any questions, I'm open to them now.
Thank you, Arjun. Yes, I would now go to the audience if anyone has any question. Maybe I'll start because I had some difficulty following what exactly is going on. It seems there's a lot of math, particularly the discrete exterior calculus is something that I don't follow. So Arjun, can you actually kind of tell me what is exactly the need of the discrete exterior calculus in this framework? Where does it come in, and what is the need of it? Maybe it is probably there also in this paper by Nathaniel Trask, as you say.
Yeah, so essentially the idea is that I'll just go back to the slide. Yeah, so the idea is that you can construct your gradient, curl, and divergence operators through these with the entire discrete exterior calculus framework in mind, using these co-boundary and boundary operators as defined over here earlier. And then using those, you can represent the PD itself, or create a representation of your entire PD operator and use that as a way to solve your PD. So uh, in the actual solution, in the evaluation part, you're using those Richardson updates to update the solution, where the correction step is essentially just the residual of using our PD representation constructed through the DC operators uh, to progressively compute the solution.
My question is actually a step back. Actually, I mean, what is the need of using this discrete exterior calculus? I mean, what motivates the use? That is what I mean. So, in general, when you're solving a PD using, or if you're trying to create a surrogate model for a PD, so where does this fit in? I mean, what's the motivation of using this? Is it kind of helping us do something better, which I was not able to do earlier with the normal things?
Yeah, so with these operators, you're sort of also keeping the geometry of the domain in mind. So it's sort of inherent to the operator itself, and due to that, you're able to at least in the comparison with hints later on, you're able to see significant sort of improvements in terms of the evaluation speed uh, with respect to a traditional solver, or in the case of hint, since you're evaluating it for multiple traditional solver steps and then occasionally the deeper net as well, uh, you're able to see those a significant time improvement, because your traditional solver would have to account for the boundary, but over here your co-boundary operator is constructed in a way where it considers the boundary of uh, your domain itself.
When you say the traditional solver, so let's say if you're solving, and I think I saw that most of your domains were regular in nature, right? They were not very irregular, or was there? I think one of the examples, I think the Helmholtz equation, or which one? I think I saw that that it was a regular boundary, right? You had, I think, a two-dimensional squared kind of a grid, I believe.
Yeah, it was a regular boundary, yes, in the case
Right.
of the elasticity problem.
So, for a regular boundary, how is the geometry? So you say that this is motivated by the, I mean, your this discrete exterior calculus motivates. It was motivated by the fact that it actually also has some kind of irregular boundary, and you need to preserve the solution becomes difficult when it's an irregular boundary. That's what you're saying. And
Uh,
by is that right?
yes. So at least in this work, initially, we realized that there are quite a few computational hurdles that we would have to first overcome. So we are mostly just dealing with this as a way to evaluate whether it works in the first place, and using more irregular geometries is something that I would want to do in like maybe the next several months, for example. So that's why at least in this problem setup, we didn't consider any irregular geometries.
Okay. So I think we have debuggers. Yeah, debugger, please. You can actually unmute yourself and ask a question.
Yeah, sure. Hi Arjun, that's a very wonderful work, and I would like to just clarify about few things. Uh, mm, so what I understood when you are like comparing it with the Hin's work is that in Hin's they use that Jacobi method for the root finding, and you are just replacing that with this DC. Uh, so basically you are trying to build a better preconditioner than what they are trying to propose. Is that it, or so is it something different?
In a way, that's pretty much it. Yeah. From a method point of view, yeah.
Okay, so uh, just a question like regarding so what hints claim that they are able to handle like different frequencies or the spectral problem. Uh, mm, in their paper. But do you think that this method can handle like so the normal numerical method will handle the high frequency and your numerical solver will handle the low frequency? Is it also happening in your case as well?
Hi, Arjun. I
Okay,
think I'm not able to hear Arjun.
yeah,
Oh,
I
hello.
think
Sorry.
oh,
Yeah,
yeah.
sorry, sorry. Yeah, so that's why we considered the Poisson and Helmholtz equation of this form so that we could construct a data set with medium to high frequency data as well. And that's the those are the evaluation results that I presented later on as well. So yeah, it is able to it is efficient even for medium to higher frequency solutions.
I see. Oh, that's really wonderful actually. But do you think like uh just a food for thought that like comparing with it with like the traditional Jacobi plus neural operator based preconditioner uh, is not um, valid. Like there are other very good preconditioners out there which can make things very efficient in terms of computation as well as accuracy. Like for example, there are like I'm not a very numerical person, but there are like there are some LU factor sparse factorization that you can do, or multigrade approach are there for better preconditioning.
Yeah, so the idea was just to compare it with other hybrid methods themselves.
Mm-hmm.
Although, uh, if we were to consider other like traditional uh, numerical preconditioners, that
Mm-hmm.
isn't something that I had done like during the study, so I should check that out as well.
Oh, oh, that's great. Yeah, thank you so much.
Yeah.
Thank you, Dibakar. Uh, Rakesh, you have a question? Anybody else has any question?
No, I don't.
Okay, so Arjun, I had one more question. So I think that you were adding these corrections from a CNN, right? I saw in one of the slides here, I think you showed that you were adding,
Yes.
right?
Yeah.
So, so these correction that you're adding, would it actually, for example, in the elasticity example that you had shown, where you had a square hole in the plate,
Yes. Yeah.
if this was, let's say, a circular or maybe some kind of an elliptical hole, would I'm just thinking like, would the convolutions be useful in preserving the structure? I mean, the geometry.
Yeah, so this
If
is something I realized when I was done with these, at least these problem setups themselves, that a CNN would be restrictive in the sense of the types of geometries that we're dealing with. But a simple fix to that would be just replacing that with a smaller, like a small GNN itself. So then you can generalize for different structures. So when trying this out for more irregular geometries, that is one change that I would have to make.
I see. Okay, that makes sense. Okay. Any more questions for Arjun? If not, we'll thank the speaker. Thank you so much, Arjun, for presenting this research.
Yeah, thank
So
you so
we'll
much.
actually stop the seminar here, and we'll actually again join next week. Okay, with that, bye everyone.